Okay, I think the doorbell is at least the rate of doorbell arrivals is starting to slow a little bit. So that I usually take that as the time to start. So I'd like to welcome everyone to our faculty candidate seminar and also a silo seminar. We have with us today, all the way from sunny Palo Alto, Viet An Nguyen, who is a postdoctoral scholar in the Department of Management, Science, and Engineering at Stanford. His research interests are in large-scale decision-making under uncertainty, statistical optimization, and machine learning. He's worked on many interesting application areas as well in energy systems and data policy and analysis. He has both a bachelor's and master's from NUS in Singapore, and his PhD is from EPFL in Lausanne. We are so delighted to have him join us here today. For questions, I think it's, let's see, we have 38, 40 people now. So I think for questions, we prefer to, please feel free to ask questions during the seminar. I'll keep my eye on the chat. And so if you'd like to ask a question in the chat and it's a clarification question, I'll interrupt Viet An, and so we can and ask the questions during the talk. And there'll be plenty of time for questions at the end. So I'd like for you all to join me in welcoming Viet An Nguyen, and I'm going to turn it over to him for the seminar.
Thank you very much for having me. And I'm very happy today to share with you some of my ideas about decision analytics. I am an operations researcher who is fascinated about data and models, and I study how we can build an analytic system that can help us make more insightful decisions. And to me, an analytic system is an end-to-end human-centric pipeline that can convert any data into actionable recommendations. I started my PhD back in Switzerland studying how we can incorporate renewable energy into our power system. And this type of problem is actually very interesting because it spans very different time granularity. We were interested in solving a 50-year long-term planning for the power system. And we are also interested in solving some day-ahead scheduling that goes down to even maybe thinking about 15 minutes load scheduling. Later on, I became interested into studying the dynamic system, and the problem here now becomes studying how to do state estimation and also studying how we can do dynamic information acquisitions in the dynamic setting. I came to Stanford 2 years ago, and during my time at Stanford, I actually became interested in studying the societal impact of operations research and machine learning algorithms. And in this case, I want to push and promote for new criteria for algorithms such as bias, reducing the bias and increasing the fairness in the solutions. Throughout my research, I actually used the ideas and techniques from optimization and statistics in order to enhance the quality of our decisions. And interestingly, the field of optimal transport also lies in the intersection of optimization and statistics. Optimal transport is a very useful framework to help us comparing two distributions by finding the most efficient way to transport one distribution to another distributions. And more importantly, I'm also interested in deriving analytic systems that are fair, interpretable, and robust. My first research pillar actually studies how we can build a robust Bayesian analytic system. I proposed two different methods to estimate the likelihood in the Bayesian setting, and then I managed to combine these two results with several co-authors in order to create a robust Bayes classifiers. My second research pillar actually studies fair machine learning, where I propose a statistical test to detect if any classifier violates a certain type of fairness criteria. And then we managed to propose several machine learning algorithms that promote fairness in both the supervised learning and the unsupervised learning settings. My third research pillar actually focused on deriving a new family of statistical estimation that are robust using the ideas of optimal transport. So using the idea of Wasserstein distributionally robust optimization, we managed to propose a minimum mean square error estimation. And for the scope of this talk, I'm going to focus on the two prominent estimation setting, which is the estimation for the inverse covariance matrix and the estimation for the conditional statistics. I would quickly stop here if there's any questions. I actually have a second screen so I can see if you type in some question in the chat box, or feel free to raise your hand. So for the first part of the talk, we are going to explore how we can use the ideas of Wasserstein robustness in order to derive a robust inverse covariance matrix estimator. The covariance matrix of a random vector psi collects basic information about the spread of each component of size and also about the linear dependency among each pair of component of size. The inverse of the covariance matrix is termed the precision matrix. This terminology is very intuitive because if the variance is high, then the precision is low and vice versa. The covariance matrix appears in the formulation of many problems in science, engineering, and economics. However, it is oftentimes the precision matrix that arises in their solutions. For the first example, let's consider a linear discriminant analysis, which is an early classification method proposed by Fisher in 1936. Given several labeled training data points belonging to different classes, here represented by different colors, the goal is to predict the class of a new unlabeled data points. And in order to solve this problem, Fisher assumes that the data points in each class follows a Gaussian distribution with a class-dependent mean and a class-independent covariance matrix. The maximum likelihood classifier in this case assigns the new data point to the class that minimizes the Mahalanobis distance to the class mean. And as such, this classifier depends on the precision matrix. A second example is the portfolio allocation problem that was pioneered by Henry Markowitz in 1952. If we want to construct a portfolio of risky assets that has minimum variance, then we have to solve a quadratic optimization problem. And the input to this quadratic optimization problem is the covariance matrix of the risky asset return. This problem, fortunately, has an analytical solution that once again depends on the precision matrix. If you agree with me that the output is more important than the input, then this example suggests that it is more important to know the precision matrix than to know the covariance matrix. Unfortunately, the precision matrix is not known and it has to be estimated from the data. For this part of the talk, I'm going to assume that psi is going to be a p-dimensional random vector following a Gaussian distribution. This Gaussian distribution has mean zero and covariance matrix sigma. We assume that sigma is positive definite. The goal of this part of the talk is to estimate the precision matrix from n independently and identically distributed training samples generated from these Gaussian distributions. Arguably, the simplest estimator for the covariance matrix is the sample covariance matrix, defined as the covariance matrix of a uniform distribution supported on the training data. We are going to denote the sample covariance matrix by sigma hat. And an estimator for the precision matrix can be obtained by simply taking the inverse of this sample covariance matrix. Unfortunately, in the big data regime, when the dimension p is greater than the training sample size n, then this sample covariance matrix is not invertible. Indeed, we can see that sigma hat is a sum of n rank 1 matrices, and thus it is never invertible if p is greater than n. An alternative to estimate the precision matrix can be obtained by looking at the maximum likelihood estimation problem. Because here we are dealing with Gaussian distribution, then maximizing the log likelihood of the training data is equivalent to solving a convex optimization problem over all candidate precision matrices X. The objective function of this optimization problem is to minimize the sum of the negative log determinant of X and an inner product between X and the sample covariance matrix sigma hat. Unfortunately, this problem becomes unbounded in the big data regime when P is greater than N, and in this case, we are left without an estimator. In the small data regime, when P is smaller than N, then this optimization problem has an analytical solution which coincides with the inverse of the sample covariance matrix. And as such, we have not gained anything yet when we move to the maximum likelihood estimation setting. However, the situation changes fundamentally if we add an L1 regularizer into the objective function and obtain the graphical lasso problem. This graphical lasso problem has many nice properties. We can show that an optimizer to this optimization problem always exists, even when P is greater than N. And because the L1 regularizer induces sparsity, then the optimal solution to this problem has many elements that are zero. Unfortunately, to obtain the estimator in this case, we have to solve a non-smooth, non-linear semi-definite program. And the complexity of solving this optimization problem actually becomes very difficult when we go for high-dimensional problem. Let us now take a more systematic approach to construct the estimator. Because we are talking about the Gaussian distribution, then the Fisher-Neyman factorization theorem implies that the sample covariance matrix sigma hat is a sufficient statistics for the true covariance matrix sigma. And as such, it is also sufficient for us to consider a class of estimator that depends on the training data only through the sample covariance matrix sigma hat. If we do not have any information about the sparsity pattern of the covariance matrix or the precision matrix, and if we have no information about the rotation of the eigenbasis, then Schagler-Steins in the 1970s suggest that we should find an estimator that is rotation equivariant. An estimator is rotation equivariant if the original estimator applied to the rotated data coincides with the rotated estimator applied to the original data. It can be further shown that any rotation equivariant estimator will share the same eigenvectors with the sample covariance matrix. And as such, the estimator is obtained by simply perturbing the sample eigenvalues. This now leaves us with two important questions of why should we perturb the sample eigenvalues and how should we do it? The reason to perturb the sample eigenvalues is because the sample eigenvalues is systematically biased. Because sigma hat is an unbiased estimator of the true covariance matrix sigma, and because the maximum eigenvalue of a symmetric matrix is a convex function, it now follows from the Jensen inequality that the maximum eigenvalue of the sample covariance matrix will, on average, overestimate the true maximum eigenvalues. Using a similar argument, then we can show that the minimum eigenvalues of the sample covariance matrix will underestimate the true minimum eigenvalues. If now we use an ellipsoid to visualize the quadratic form of the covariance matrix, then by what we have seen so far, then the sample covariance matrix will flatten this ellipsoid on average. So it will stretch in the longest semi-axis and it will shorten in the smallest semi-axis. And as such, the sample covariance matrix is ill-conditioned and squeezed. And to resolve this problem, then Ledroit and Wolf in 2004 proposed to consider the class of shrinkage estimator. Now the shrinkage target is denoted by S, and what remains to be solved is to find a parameter of shrinkage alpha, and this can be done by systematically by looking at the training data. An estimator for the precision matrix can be obtained by simply taking the inverse of the resulting shrinkage estimator for the covariance matrix. And this can be done whenever S is well conditioned and invertible. Alternatively, we can also use a lot of other techniques, for example, using nonlinear shrinkage of the eigenvalues and using a condition number regularization, or we may resort to some factor models. The discussion so far suggests that a good estimator for the precision matrix should have these following properties. First, the estimator should exist even in the big data regime when p is greater than n. It should be rotation equivariant, which means that it should preserve the eigenvectors and perturb only the sample eigenvalues. But at the same time, it should also preserve the order of the sample eigenvalues. The estimator should be well conditioned and easy to compute. And most importantly, the estimator should be close to the true precision matrix, and it should be derived from intuitive and fundamental principles. Let me quickly stop here to see if there's any questions.
I'll ask a quick question. So, I mean, if I can, so why is it, I mean, preserving the order of the eigenvalues, why is that is that more or less important than actually just being close to the actual true precision matrix? Does the order, why, maybe showing my ignorance here, but why is the order of the eigenvalues so important?
The order is important because it basically tells you how important each of these subspace is. So the higher the eigenvalues means the more important the subspace. So somewhat later on, we want to do PCA, for example, then PCA most likely is done by taking the subspace that correspond to the maximum eigenvalues, for example, then we don't want to perturb that order in some way.
I see, but yeah, but I mean, they're related, of course, in the sense of like that won't it be true that if you, it's hard to get a close matrix if the order of the eigenvalues, swaps around, right?
Yeah. Somehow all of these conditions are intertwined together. So possibly by deriving a estimator that is close to the true inverse of the covariance matrix, then most likely we will preserve the same order. So.
Okay, thank you.
All right, so the first part of the talk, we are going to explore a systematic approach to construct the estimator for the precision matrix. And to do so, we are going to use the Stein's laws in order to quantify the quality of the estimator. Unfortunately, this Stein's loss function is not available in practice because it involves an inner product between the true covariance matrix sigma and the decision variable x. However, this inner product can be rewritten as an expected form of a quadratic function under an unknown distribution P. And in doing so, now we have a stochastic program with an unknown probability measure. And it has been suggested that a good quality solution to this type of problem can be obtained by taking the distributionally robust optimization approach. And this motivated us to consider to minimize the worst case Stein's loss over all distribution Q lying in some ambiguity set. And this ambiguity set is a ball of radius rho centered at the nominal distribution, defined as a Gaussian distribution with mean zero and covariance matrix sigma hat. Now this minimax estimation problem has many nice properties because if we set the radius rho equals to 0, then we simply recover the nominal maximum likelihood estimation problem. And as such, the model I'm writing down here can be considered as a robustification of the maximum likelihood estimation setting. So this part of the talk, we're going to use the type 2 Wasserstein distance and the squared Wasserstein type 2 distance between Q1 and Q2 can be thought of as the minimum transportation cost of moving Q1 to Q2, where the cost of moving a point mass is given by the squared Euclidean distance. And because we are going to focus on the family of Gaussian distribution, then it is very lucky for us that the Wasserstein type 2 distance between Gaussian distribution is known in closed form. Given two Gaussian distribution with mean zero, then the distance between them can be written in a closed form that involves only the covariance matrices. And this formula here, even though it looks a bit complicated, this formula here is going to be very crucial for our subsequent analysis. Now we can rigorously define our ambiguity set as a ball in the space of Gaussian distribution that has radius rho centered at the nominal distribution. And it is important to notify that this ambiguity set contains only Gaussian distribution, and it is actually non-convex. Indeed, if we take two Gaussian distribution and then we take a mixture of two Gaussian distribution, then in general, the mixture is not a Gaussian distribution anymore. Right. For the rest of the talk, I'm going to show to you, for the rest of this part, I'm going to show to you that this type of minimax estimation problem has many nice properties. So first of all, we can use a limit law for the empirical Wasserstein distance between Gaussian distributions, and we can tune the radius rho in such a way that the true distribution P belongs to the ambiguity set with a high probability. And as such, the optimal value of our estimation problem will constitute an upper confidence bound on the true Stein's loss under the true but unknown distribution P. Secondly, whenever the radius rho is strictly greater than 0, then we can show that the estimation problem is equivalent to a nonlinear semi-definite program. We can further show that this semi-definite program is always solvable when even in the big data regime when P is greater than N. And even though this formula is very nice, it turns out that we have a lot of troubles trying to scale up this problem to high dimensional problems. But it was once again very lucky for us that this semi-definite program has many nice properties, and an analytical solution exists for this problem. We can show that the optimal precision matrix estimator will share the same eigenbasis with the sample covariance matrix, and its eigenvector, its eigenvalues xi star can be obtained by a nonlinear transformation of the corresponding sample eigenvalues. This nonlinear transformation involves only one parameter gamma star, and gamma star can be found by solving a nonlinear algebraic equation written on the bottom of the slide. In doing so, we have shown that our estimator actually is rotation equivariant. Furthermore, each eigenvalues is strictly positive, and as such, our estimator is also invertible. And most importantly, this estimator is extremely easy to compute because we only need to find a spectral decomposition of the sample covariance matrix sigma hat, and then we can apply a bisection in order to find gamma star. We can further show that our estimator belongs to the class of a nonlinear shrinkage estimator, and we thus refer to it as the Wasserstein shrinkage estimator. This estimator is going to shrink the sample eigenvalues down to 0, but at the same time, it also preserves the order of the sample eigenvalues. We can also show that the condition number also improves as the radius increases. And now we start to benchmark our estimator against some of the existing estimator that can be found in the literature. So we are going to compare the performance of our Wasserstein shrinkage estimator against the linear shrinkage and the graphical lasso that I have introduced earlier. In the first part, we are going to benchmark using the classification setting on two medical data set with the extremely low number of sample size. And the bottom on the table on the bottom of the slide actually indicates the correct classification rate on the test data. And we can see that the Wasserstein shrinkage estimator performs actually very well on this correct classification rate, and especially in the big data regime when P is actually higher than the number of samples. We also benchmark our estimator on the portfolio allocation problem using the Fama-French dataset. In this case, actually the graphical lasso estimator is going to produce a portfolio that has minimum variance. However, it is our Wasserstein shrinkage portfolio that has highest mean return, and also surprisingly the highest Sharpe ratio in terms of the return. Now let me quickly wrap up this section by highlighting to you once again all the desirable properties of our estimator. The Wasserstein shrinkage estimator actually exists even in the big data regime when p is greater than n. The estimator is rotation equivariant and it preserves the order of the sample eigenvalues of sigma hat. Furthermore, the condition number also improves, and the complexity of computing this estimator is extremely easy because it involves only a spectral decomposition of sigma hat, and then a bisection can be used to find the gamma star. I would like to emphasize once again that all of these nice properties are not imposed ad hoc, but they arise naturally from a coherent robustification of the maximum likelihood estimation problem. Now, there may be some questions of like, why should I use a Wasserstein type 2 distance to construct the ambiguity set? And I think that an instructive way to answer this question is to consider how the estimator will look like if we use other construction of the ambiguity set. And we can show that for other construction of the ambiguity set using either the Kuhnbeck-Labler, the Fischer-Rao, and other variants of the Wasserstein distance, then we will not get the same nice result. So all of these alternatives to construct the ambiguity set will suffer either from the singularity issues, the well-posedness issues, or the computational issues. That will be the end of the first part on the inverse covariance matrix estimation. And I would like to quickly stop here if there's any questions.
I had a quick question, Rob, here. I was wondering, this Wasserstein distance has a very nice interpretation in terms of covariances when everything's multivariate normal. And I was wondering just what you can say about robustness to deviations from normality.
So actually my thesis is about how we can upper bound that deviation. So we can show that for this type of problem, because we have a quadratic we have an expectation with a quadratic function, then actually if you start with a nominal distribution that is Gaussian and the ambiguity set contains all the weird distribution that you may think of, like uniform, then the worst case distribution is still a Gaussian distribution.
Cool.
So
yeah,
you can think of the
yeah.
radius rho as the amount of energy that the nature can have. And it turns out that the nature will not change the parametric form of the distribution, but the nature will change only the mean and the covariance matrix. So,
gotcha.
So even though we give the nature the possibility to go to other families, the nature will not do that because it takes so much energy to reshape the distribution to another parametric family.
Interesting. Thanks. Yeah, that's cool.
So somehow that result is based on the fact that we have a quadratic function, and then the Wasserstein type 2 is also Euclidean and Gaussian. Euclidean, and then we have a squared and everything. So everything seems to match very well for type 2. That's it. All right. So for the second part of the talk, I'm going to show to you how we can use the ideas of the Wasserstein robustness to construct a robust estimator for some non-parametric estimation settings. So in this part, we're going to focus on a p-dimensional random vector psi, and we are also equipped with some d-dimensional contextual information omega. For example, we may consider our a traffic network that connects our homes to the university. And the random vector size here may encapsulate the travel time on each edge of this network. And clearly this travel time should be dependent on the weather, which is represented by omega. For example, if the weather is nice and sunny, then our travel time to the university may be very short. However, if it is snowy, then it may take us longer to get to the university. Now, if our goal is to devise a routing plan that brings us from home to the university with a minimum expected travel time, then it is also beneficial for us to take the weather into account in order to make better decisions. In this case, because we are interested in minimizing the expected travel time, then we will need to estimate the conditional expected travel time given the weather is sunny or the weather is snowy. A lot of decision-making problems and machine learning problems can also be formulated as a decision-making problem with contextual information. For example, we may look into a digit label prediction setting where the input here is a grayscale image, and the label psi is going to encapsulate which digit is represented by the input. And the goal is to predict the digit given any grayscale image. And one way to do this type of prediction is simply to compute the expected value of the digit label for each input. And these type of problems actually highlight the importance of actually computing the expected value, the conditional expectation for many learning and decision tasks. And this conditional expectation is also known in the statistics community as the regression function. If we define the regression function by psi star, then psi star is a measurable function that maps any input omega into a prediction of psi. We also know that psi star is a minimizer to the minimum mean square error estimation problem, where the expectation here is taken with a joint distribution of psi and omega. However, solving this type of problem is extremely difficult because it is an infinite dimensional problem, and it is only tractable under very strong assumptions of P. For example, like if we assume that P is a joint Gaussian distribution. So for this part of the talk, we are going to focus on a much simpler problem where we are going to estimate the conditional expectation for a fixed value of input omega 0. In doing so, now we have converted the problem into a finite dimensional optimization problem. However, this type of problem is still challenging because we don't know the true distribution P, and we have only access to some training data, which is highlighted as a red triangles in this graph. There's still another very tricky issues here because we actually may not have any observations with the exact covariate of omega 0. And as such, identifying the conditional expectation or the conditional distribution is a very tricky problem in the data-driven setting. To resolve this problem, we are going to borrow some of the ideas from the field of non-parametric statistics. And we are going to consider a lot of non-parametric estimator can be written as a weighted local averaging estimator. And the weighting function W here will represent the normalized weight of a training sample I when that training sample is used to compute the estimate. If we change the weighting function W, then we start to have a lot of different family of estimator. For example, a special instance is the k-nearest neighbor estimate. And in this case, the weighting function has a value of 1 over k if the covariate omega hat I is one of the k-nearest neighbor to the value of omega 0. For example, if I fix k equals to 2, then this estimator will first identify two data points that are closest to omega 0 in the omega space. And then the estimate is simply computed by taking the average of these two data points in the psi space. From the construction of this type of estimator, we can easily see that the estimate will be highly dependent on the local structure of the data. And as such, there may be some attack or there may be some perturbation to the training data, and this may lead to a very bad performance of the estimator. And there has been a emerging stream of literature that tries to robustify this type of estimate. And it can be divided into three types of strategies. The first strategy is the global pruning approach, where we try to remove the outliers from the training data, and then we train a new estimator from the clean data set where the training samples from different labels are far away from each other. A second approach is by trying to augment the data set by like injecting more of these adversarial examples into the training data. However, it is unclear how we can generate adversarial examples for non-parametric estimator, and the literature has been focusing mainly on the one nearest neighbor approach. There's also a emerging stream in the field of operations research where we want to build a robust decision-making procedures using site information. When we convert this type of problem into the conditional estimation problem, then it boils down to a two-step procedures. First, we need to find the nearest neighbor that are close to omega 0, and then we compute the worst case estimator by perturbing only in the side dimensions. This approach, unfortunately, does not perturb in the omega space, and actually in the real world examples, then it looks much different than this, because I can take a image classification problem here, where the columns to the left actually represent the input image, and the 5 images to the right are going to be the 5 nearest neighbors. If we look into the to the top row, then we have an original image, a clean image of a bunch of swans. And then the 5 nearest neighbors actually contains 4 images of the swan. However, if we start to inject some noise into the problem, into the input, then in the middle row, we can see that there are no nearest neighbor that contains an image of a swan. And in the high distortion setting, when there's a lot of noise, then all the 5 nearest neighbors do not even contain any image of a bird. So this example highlights that the nearest neighbors can be easily fooled. And then if the nearest neighbors are wrong, then it's quite clear that the estimate can also be wrong. Let me quickly stop here if there's any questions. All right, so the motivation for us to start this project is how can we build a robust estimator that can somehow mitigate these kind of effects when we have uncertainty in the input image. And our construction of the estimator will rely on the 2 distinctive features. First of all, we are going to consider a more general conditional minimum mean square error estimation problem, where instead of conditioning on a fixed set of omega 0, we are going to condition on a fiber set. This fiber set represents the event that omega belongs to a ball of radius epsilon around the input omega 0. And now if the expectation is taken with the empirical distribution, then epsilon can be thought of as a parameter, and we can tune this parameter epsilon so that we can get exactly the same output as the k-nearest estimate. Secondly, we are going to consider the robust optimization approach, where we are going to minimize the worst case conditional expected loss. Here we have to add a strictly positive constraint into the feasible set of the supremum problem, because we need to avoid conditioning on a set of measure 0. The ambiguity set in this case is constructed as a ball of radius rho centered at the empirical distribution. This empirical distribution now is non-parametric, and it is defined as a uniform distribution supported on the training data points. This estimation problem is also very appealing, because if we set the radius rho equals to 0, then we simply recover the k-nearest neighbor estimate. And as such, we can think of this problem or of this model as a robustification of the k-nearest neighbor estimator. In this part, we're going to use the type infinity Wasserstein distance to measure the dissimilarity between 2 distributions. We need to impose a small assumptions here that the ground matrix is separable into a norm in the omega space and plus a norm in the psi space. Now the ambiguity set can be constructed as a non-parametric ambiguity set centered at the empirical distribution with radius rho. And for a visualization, then we can see that this ambiguity set will contains all the distribution that is obtained by simply spreading the mass from the red triangles to the corresponding blue diamonds. And as such, this ambiguity set is completely non-parametric. Now we can use some statistical guarantee of the type infinity Wasserstein distance. And now we can tune the radius rho in such a way that the true distribution P belongs to the ambiguity set with a high probability. And if we do so, then the optimal value of the optimization problem that we solve will constitute an upper confidence bound on the conditional expected loss under the true distribution. Next, we are going to explore how we can find the estimate. If we define the f of x as the worst case conditional expected loss, then evaluating f of x is equivalent to solving a supremum problem. For a case that I have drawn specifically here, then we can see that the blue diamonds do not intersect with the green fiber. In this way, we can see that there is no distribution Q that is feasible for the supremum problem. And as such, the supremum problem here is ill-posed. Now, if we define kappa I as the minimum distance between the training samples to the green fiber set, then we can show that the supremum problem here is well defined if rho is bigger than the minimum values of kappa I. And only in this case that the value f of x is somewhat sensible. Moreover, the nature of the conditioning action implies that there will be only a subset of these data points that are relevant to our optimization problem. Those are the data points whose blue diamonds actually intersect with the green fibers. And those corresponds to the samples that fall inside the blue region as drawn in this slide. Those samples that fall outside of this blue region can be safely discarded because they are not relevant to the optimization problem. Moreover, there will be some data points whose blue diamonds lies strictly inside the green fiber. And those are the trapped samples. And for the remaining samples, we are going to call them the remainder samples. Using this categorization of the relevant samples, we can show that evaluating f of x can be written as a fraction that involves the values of alpha I and vi star. Now the value of vi star is equivalent to the worst case expected loss of each individual sample points I. And the value of alpha I is going to indicate whether I should compute or I should use the sample I's in the evaluation of the worst case loss. The expression for alpha I's is a bit complicated, but it simply means that the sample I should be counted if I is a trapped sample, or if counting I actually increase the average loss. With this result, then we can easily evaluate the value of the function f of x if we know how to evaluate the fi star. And now we can start solving for x by using some convex optimization approach. And if x is one-dimensional problem, then we can simply use some golden section search. And for multi-dimensional problem, we can simply use some subgradient descent, or for special cases, we can also reformulate it as a second order cone problem. Now we start to benchmark our estimators in a handwritten digit regression problem. So the input image is going to be a 28 by 28 grayscale image, and we allow for a prediction in the real value range from 0 to 9. The two graphs that are drawn on the bottom of the slides actually represents the absolute estimation error and actually the empirical distributions of the absolute estimation error for different training sample size. If you look into the bottom curve, then actually it is a green curve representing the error of the k-nearest neighbor approach. And the curve in the middle, which is like an orange curve, is going to be the approach that is robust by perturbing only in the psi dimension, which means perturbing only in the label space. And these red arrows here actually show the improvement by taking into account this perturbation on the psi space. Our approach actually take into account the perturbation in both omega space and the psi space, and it gives a better improvement over the vanilla k-nearest neighbor approach. And this somehow justifies the merits of our approach. We also want to see how our different estimators is going to perform if we start perturbing the input images. So to do this, we are going to pick 2 random images from the training data set, and we are going to interpolate between them using optimal transport barycenter, the Wasserstein barycenter. And now the numbers on top of each image is going to tell us the prediction that is given by each method. And we can see that for our method, which is in blue, then we managed to stick to the value of an 8 for the image to the right. And similar behavior actually persists in other examples. For example, here, our estimator actually managed to stick to the value of a 6 if we simply perturb the input image a little bit. Now, let me quickly wrap up this section by highlighting once again all the nice properties of our non-parametric estimator. And our estimator is obtained by a simple and coherent robustification of the k-nearest neighbor estimate. And it is designed in such a way that it can hedge against the nearest neighbor misidentification. And all of these properties is actually obtained by simply by a coherent robustification of the original problem. Now there's a standing questions of why should I use the type infinity metric? And to resolve these problems, it is also instructive to look at how the estimator will look like under other constructions of the ambiguity set. We can see that for any other construction of the ambiguity set is either using the Kuhnberg-Leibler or any other Wasserstein distance. It will lead to some very trivial solution. And the way to construct a trivial solution is by picking any data points, and then we simply split the mass to a portion of delta and move that point to the green fiber set. And because I can set delta to a very small value, then I can move this delta to anywhere on the green fiber set. And as such, the value of f of x in this case will be simply an optimal value of a robust optimization problem. This robust optimization problem turns out that it depends only on the support of the psi, and it does not depend on the training samples. So we completely lose the ideas of data-driven or statistical estimation with the data. So that's why it becomes trivial. And it seems like up to now, this is the only way to, the type infinity is the only way to generate some simple estimator in a coherent approach. Well, let me quickly stop here to see if there's any questions.
No?
Yep. All right. So for this talk, I have actually, we have actually explored how we can construct a robust estimator for the inverse covariance matrix and the conditional statistics. It turns out that the two approaches are completely different. So in the first part, when we talk about inverse covariance matrix, we went totally parametric. We go for Gaussian and maximum likelihood estimator. In the second case, when we talk about conditional statistic, the approach is totally non-parametric, and somehow like these two problems complement each other very nicely. However, let me also say that the landscape of this type of Wasserstein statistical estimators is also much bigger than this. We can show that the same idea of Wasserstein robustness can be applied to minimum mean square error, to Kalman filtering, and also to construct the likelihood values. This is what we have known so far. So what would be the future? I believe that the data is very messy and dirty, and I think that the future has to be dealing with a lot of these missing values and anomaly detection in the input data. And together with several of our industry collaborations, we are exploring how to deal with these type of anomaly and missing values in a structured manner. I also believe that we should have a lot of new approaches to model and handle the new types of data. Those are the data that comes from rare or extreme events, or it may come from a non-Euclidean data. From the post-processing side, I believe that we should be much better at detecting distributional shift and how to handle distributional shift. I also believe a lot that there should be there should be a new way to detect and correcting errors regarding to fairness and how to promote inclusive solutions in the operations research models. To me, these are the 6 blocks, and we can actually also combine in a combinatorial manners to generate new problems. And these type of problems will be a fundamental building blocks to somehow generate an analytic system that can map any data into actionable recommendations in a human-centric and application-driven manner. Thank you very much.
That was great. Thank you so much, Vietnam. I see we have some clapping going on. Either does anybody have? But we also do have some time for questions. If people have questions about the work, I have one actually. Maybe just to get started. So so I understand. So in the first part, when you were estimating the covariance matrix, you said that there were, of course, I mean, it's a great advantage to use the type 2 Wasserstein because you were able to show that it leads to this closed form solution. And so everything can be computed quickly. And it turned out that it was a good estimator in beating graphical lasso and those types of things. You alluded on one slide that you could have tried, at least in some contexts, a different Wasserstein type, but it wouldn't be, there wouldn't be a closed form solution. You might actually have to solve an optimization problem to get the estimator. Has anybody tried that? Do you get a good estimator? Is there reason to believe that it might be a good estimator, even if you didn't have a closed form solution?
No, I have not seen any papers doing that.
Okay.
But I think the approach should be quite straightforward. So robust optimization is a very easy way to handle this, right? So you formulate the original problem, you robustify it, and then you find the dual of that, right? So from a min max, you convert it into a min, and then that should be doable.
Great. Are there other questions for Vietnam? I don't know if I can see everybody. It's a big crowd. Okay, if there's no other questions, I'm going to unmute and I'm going to clap and say thank you very much for just an excellent talk, sort of like tying some very different ideas together, but under sort of like a somewhat common umbrella. It's very interesting to see all the different things that you can do. So a few of us, this concludes the formal presentation. A few of us, faculty especially, might hang out for a few minutes afterwards. So Vietnam, if you want to take like a short break, you maybe just take like a 2 or 3 minute break, and maybe we'll reconvene back here maybe at 5 o'clock on the nose, and we'll just keep the Zoom line open, and we can just chat, about maybe. We can still talk about technical things if you want, but we can maybe have a less technical conversation as well. Sound good?
Oh, I don't need a break. I can start right away.
Oh, okay. Well, let's just, I need a
Just
short
sit
break.
down.
Yeah, just